What specific problem does your proposed methodology of tracking AI progress via the task completion time horizon aim to solve, and what limitations in existing benchmarks does it address?
The proposed methodology of tracking AI progress through the task completion time horizon aims to solve the problem of effectively measuring and comparing AI capabilities across different models and benchmarks. Existing benchmarks often consist of artificial tasks that do not reflect real-world economic value, and they are biased towards tasks that current models struggle with, leading to a saturation of individual benchmarks. Additionally, there is a lack of a unified quantitative metric to compare models of vastly different capabilities, which hinders meaningful assessments of AI progress. By operationalizing the time horizon as the duration of tasks that models can complete at a certain success probability, this methodology provides an intuitive and continuous measure of real-world capability, addressing the limitations of existing benchmarks that fail to capture the dynamic nature of AI performance. Ultimately, this approach allows for a more accurate understanding of AI advancements over time, particularly in economically valuable tasks.
Can you explain how the proposed methodology works? Illustrate the steps involved in measuring the X% time horizon and how you estimate task completion durations for AI models.
The proposed methodology for measuring the X% time horizon involves several key steps. First, we convert the performance of AI models on various tasks into binary success or failure values, often using a task-specific threshold to determine success. Next, we utilize logistic regression to model the relationship between task difficulty, measured by human completion time, and the probability of success for each model. Specifically, we estimate the 50% time horizon by identifying the task duration at which a model has a 50% chance of success, using the geometric mean time of successful human baselines as the difficulty rating. This process is repeated for different success probabilities, e.g., 80%, to derive corresponding time horizons, allowing us to track AI capabilities over time. Ultimately, we find that the 50% time horizon has been growing exponentially, with a doubling time of approximately 7 months from 2019 to 2025.
Can you provide a simple illustrative example that shows how you apply your method to evaluate an AI model's performance on a specific task, detailing each step from task selection to result interpretation?
To evaluate an AI model's performance using our method, we first select a specific task from our dataset, such as a software engineering task from the HCAST suite that requires a human expert approximately 2 hours to complete. Next, we establish a baseline by measuring the time taken by skilled human baseliners to complete this task, which we record as the geometric mean of successful attempts. We then evaluate the AI model on the same task, scoring its performance based on whether it meets a predefined success threshold, which is determined by the human baseline performance. After collecting the AI's success rates, we apply logistic regression to estimate the task completion time horizon, specifically the duration at which the AI model has a 50% chance of success. Finally, we interpret the results by comparing the AI's time horizon against the human baseline, noting any trends in performance over time, such as whether the AI's capabilities are improving relative to human performance on similar tasks.
What are the theoretical or practical benefits of using the time completion horizon metric over traditional benchmarks, specifically in terms of its ability to provide insights into real-world AI capabilities?
The time completion horizon metric offers several theoretical and practical benefits over traditional benchmarks. Firstly, it provides a continuous and intuitive measure of AI capabilities by quantifying the duration of tasks that models can complete at a specified success probability, which is more reflective of real-world performance than static benchmarks that often focus on artificial tasks. Secondly, this metric allows for meaningful comparisons across models with vastly different capabilities, addressing the limitations of traditional benchmarks that saturate quickly and do not facilitate cross-benchmark analysis. Additionally, The time horizon metric has shown exponential growth trends, indicating significant advancements in AI capabilities over time, which can be directly correlated with human performance metrics. Lastly, by incorporating task completion time as a proxy for difficulty, the time horizon metric aligns more closely with the complexities of real-world tasks, thus providing better insights into how AI systems might perform in practical applications.
How did you validate the effectiveness of your proposed method? Describe the datasets, benchmarks, and metrics used in your experimental design and what results you derived from them.
To validate the effectiveness of our proposed method for measuring AI capabilities through task completion time horizons, we utilized three distinct datasets: HCAST, REBench, and the newly developed Software Atomic Actions (SWA) suite. HCAST consists of 97 diverse software tasks, REBench includes 7 challenging ML research engineering tasks, and SWAA comprises 66 short tasks designed to capture single-step actions in software engineering. We benchmarked 13 frontier AI models from 2019 to 2025 on these tasks, calculating the 50% time horizon, which we found to be growing exponentially with a doubling time of approximately 7 months. Additionally, we conducted supplementary experiments to assess external validity, including replicating our methods on SWE-bench verified, which confirmed a similar exponential trend, albeit with a shorter doubling time. Our results indicated that while AI performance improved significantly, challenges remained in less structured, messier tasks, highlighting the need for further exploration of real-world applicability.
What limitations did you identify in your methodology, particularly in terms of analyzing AI capabilities in the context of real-world tasks and their implications for future AI developments?
In our methodology, we identified several limitations regarding the analysis of AI capabilities in the context of real-world tasks. Firstly, the tasks used in our benchmarks, such as SWAA, HCAST, and REBench, are systematically different from real-world tasks, lacking elements like interaction with other agents, resource constraints, and the need for high reliability, which are common in practical scenarios. Secondly, our tasks are automatically scored, which reduces the open-endedness and complexity typically found in real-world tasks, potentially skewing the results. Additionally, we noted that our human baseliners, who are highly skilled professionals, may not represent the average employee's performance, leading to discrepancies in task duration estimates. Lastly, while we observed exponential growth in AI capabilities, the generalizability of these trends to real-world tasks remains uncertain, suggesting that our benchmarks may not fully capture the complexities and messiness of actual work environments.